From space, it appears as a tranquil oasis, an extraordinary blue marble teeming with life, but down on the surface, a different story is unfolding. Our planet is warming at a rate unprecedented in human history. This isn't a distant threat, it's the reality of our time, written in the language of scorching heat waves, devastating wildfires that turn skies orange, and supercharged storms that unleash catastrophic floods. Ecosystems, from vibrant coral reefs to ancient rainforests, are buckling under the strain, pushing countless species towards the brink. For decades, the scientific consensus has been clear. The culprit is the invisible blanket of greenhouse gases, carbon dioxide, methane, and others we have relentlessly pumped into the atmosphere. This heat-trapping layer, a byproduct of our industrial civilization, is disrupting the planet's delicate energy balance. The fundamental solution is equally clear: we must drastically reduce these emissions. This means transitioning our global economy away from fossil fuels, embracing renewables, and reforesting our lands. We have the roadmaps, but global cooperation has proven tragically slow. And so, as the window to avert the worst impacts narrows, a radical and deeply unsettling conversation is moving from the fringes of science to the halls of power. With the planet's fever rising and our primary treatment plan lagging, some scientists are asking a difficult question. Is it time to consider a planetary emergency intervention? They are looking to the skies not with hope, but with a proposal for a deliberate large-scale manipulation of the Earth's climate. A Plan B that is as audacious as it is terrifying. This is the world of solar radiation management, or solar geoengineering. For a long time, it was the stuff of science fiction, a concept so fraught with peril it was considered taboo. The core idea is deceptively simple. If we can't remove the heat-trapping blanket fast enough, perhaps we can turn down the heat source. Solar geoengineering doesn't address the root cause, the buildup of CO2. Instead, it aims to treat a dangerous symptom, excess heat. It proposes to deliberately reflect a tiny fraction, just 1 or 2% of incoming sunlight back into space, enough to offset the warming from our emissions. Several methods have been proposed, from brightening clouds over the ocean to placing mirrors in orbit, but the most studied technique is stratospheric aerosol injection. This involves spraying microscopic, reflective particles into the stratosphere, about 12 to 30 miles above the surface. Here, the particles would linger for a year or two, scattering sunlight and creating a thin planetary haze. We have a natural blueprint for this process, a powerful volcanic eruption. In 1991, Mount Pinatubo in the Philippines erupted, blasting 15 million tons of sulfur dioxide into the stratosphere. This gas formed a cloud of sulfate aerosols that spread around the globe. The effect was profound. For the next 2 years, the planet cooled by an average of 0.5 degrees Celsius, temporarily pausing global warming. It also produced a side effect: stunningly vibrant sunsets as the particles scattered the evening light. Pinatubo became an unintended planet-wide experiment, proving the basic principle of stratospheric cooling works. The modern proposal for stratospheric aerosol injection seeks to replicate the Pinatubo effect in a controlled, sustained manner. Instead of a volcano, a fleet of specially designed high-altitude aircraft would make regular flights, releasing a calibrated amount of aerosols. The goal is to create a man-made invisible shield, a planetary parasol, that could be adjusted to gently dial down the sun's intensity. It's a breathtaking concept, humanity taking direct control of the planetary thermostat. But intervening in a system as complex as Earth's climate is an act of immense consequence, filled with unknown risks and ethical dilemmas we are only just beginning to comprehend. Our story begins with a force of nature, In 1991, Mount Pinatubo in the Philippines erupted with staggering power, an event that would unexpectedly provide a blueprint for one of humanity's most audacious and controversial ideas. The eruption was immense, ejecting cubic miles of rock and ash, but its most globally significant payload was invisible: 20 million tons of sulfur dioxide gas. This colossal plume didn't just linger near the ground, it was blasted more than 20 kilometers upwards, punching through the troposphere, the atmospheric layer we live in, and into the serene, stable realm of the stratosphere. This distinction is critical. In the troposphere, rain and weather would have washed these pollutants out in a matter of weeks, but in the stratosphere, a different fate awaited them. High above the clouds, a slow and steady chemical transformation began. The sulfur dioxide gas reacted with water vapor, converting into a mist of microscopic sulfuric acid droplets. These are sulfate aerosols, particles so minuscule and lightweight that they could defy gravity, remaining suspended in the stratosphere for years. They are far too small to be seen individually, but collectively they formed a vast planet-encircling haze. From the ground, the effect was subtle but beautiful, producing a series of breathtakingly vibrant sunsets and sunrises around the world as the sun's rays passed through this new stratospheric layer. But the most profound effect of this aerosol veil wasn't what it did to the light we saw, but what it did to the light we didn't. These particles are the perfect size to scatter incoming sunlight, particularly in the ultraviolet spectrum. They act like a planetary sunscreen, reflecting a small but significant portion of solar radiation back into space before it can reach and warm the Earth's surface. The effect was not theoretical, it was measured, tracked, and analyzed by satellites and weather stations across the globe. In the 2 years following the Pinatubo eruption, the Earth's average temperature temporarily dropped by about 0.5 degrees Celsius, or nearly 1 degree Fahrenheit. This single volcanic event temporarily paused the steady march of global warming, offering a powerful, real-world demonstration of what is now known as solar radiation management. This leads to a monumental question. If a volcano can do it by accident, could we do it on purpose? This is the core premise of stratospheric aerosol injection, or SAI. The concept is to intentionally replicate Pinatubo's cooling effect, not with a violent eruption, but with a carefully controlled, continuous deployment. The most studied method involves a fleet of specialized aircraft engineered to fly at altitudes of over 65,000 feet, far higher than commercial airliners, to deliver a steady payload of sulfur dioxide, or perhaps a more advanced precursor material. Other, more speculative proposals include using giant tethered balloons to pump aerosols up through long hoses, or even firing shells from massive artillery cannons. The scale would be immense, requiring thousands of flights every year, year after year, to maintain this thin protective veil. The research goes far beyond just sulfur. Scientists are actively exploring alternative materials that might be more effective or have fewer negative side effects. For instance, some studies suggest that calcium carbonate, essentially chalk dust, could cool the planet while also helping to repair ozone damage, a major concern with sulfur-based aerosols. Others have even modeled the effects of using diamond dust, which is highly reflective and chemically inert. This careful step-by-step research is crucial because while our computer models are incredibly sophisticated, they are no substitute for real-world observation. Projects like Harvard's now cancelled Stratospheric Controlled Perturbation Experiment, or SCOPEX, were designed to be a first step in this direction, not to deploy geoengineering, but to release a tiny, non-toxic amount of material from a balloon to test how it behaves in the real stratosphere, providing invaluable data to refine our models. And those models reveal a deeply complex picture, filled with profound risks. While SAI could lower the global average temperature, the cooling would not be uniform. Some models predict it could dramatically alter regional weather patterns, potentially weakening the Asian and African summer monsoons, which provide water for agriculture that feeds billions of people. There is also the significant risk of damaging the ozone layer. While newer materials like calcium carbonate might mitigate this, using sulfur, the material we have the most data on from volcanoes, would almost certainly cause some level of ozone depletion, increasing the amount of harmful UV radiation reaching the surface. Perhaps the most terrifying risk is what scientists call termination shock. SAI is not a permanent fix, it's a temporary treatment that masks the symptoms of climate change. If a global SAI program were ever started and then abruptly stopped due to war, political disagreement, or economic collapse, the warming that had been suppressed would emerge with terrifying speed. The planet could experience decades of warming in just a few years, a rate of change so fast that ecosystems and human societies would have no hope of adapting. Furthermore, SAI does nothing to address the root cause of climate change, the buildup of carbon dioxide in the atmosphere. Even under a cooler sky, CO2 would continue to dissolve into the oceans, driving ocean acidification and threatening the entire marine food web, from corals to shellfish. It's a technology that forces us to confront a world of cascading consequences, where the line between a solution and a catastrophe is perilously thin. The most compelling argument for exploring solar geoengineering is its potential as a global emergency brake, as we risk crossing critical tipping points. In such a dire scenario, it could offer a way to rapidly cool the planet, buying precious time and preventing the worst-case outcomes. This cooling effect could bring profound benefits, particularly for the most vulnerable ecosystems and human populations. However, this promise is shadowed by immense risks. Artificially scattering sunlight could disrupt regional weather patterns, potentially shifting vital monsoons. Furthermore, solar geoengineering does nothing to address ocean acidification, a corrosive threat to marine ecosystems and coral reefs. There is also the danger of termination shock. If the system suddenly failed, the planet would experience all the suppressed warming in just a few years. As we stand at this precipice, the path forward is anything but clear. The very idea of solar geoengineering has fractured the scientific community, creating a chasm of debate that is as deep and complex as the climate system itself. The scientific community itself is deeply divided. On one side, there are the cautious pragmatists. They argue that ignorance is not a defense. Proponents argue we must understand this tool, even if we hope never to use it. They see research not as an endorsement, but as a vital form of planetary insurance. Their position is that in a world facing potential climate tipping points, we cannot afford to be flying blind. We need to know if this emergency brake is a viable option or a far greater hazard than the problem it seeks to solve. They advocate for controlled, small-scale and transparent experiments to test the efficacy and risks, to see if our sophisticated computer models hold up in the real world. They believe that only through rigorous research can we arm future generations with the knowledge to make an informed choice should the worst-case climate scenarios come to pass. On the other side of this divide, there's a chorus of loud and urgent opposition. These scientists and ethicists warn of a moral hazard. They fear that the mere existence of a perceived technological fix, a plan B, will inevitably weaken our collective resolve to tackle the root cause of the crisis, greenhouse gas emissions. It's a seductive, dangerous promise of an easy way out, which could divert critical resources and political will away from the difficult, necessary work of decarbonizing our economy. Opponents also raise the specter of unintended consequences, arguing that we are dealing with a system of near infinite complexity. To believe we can safely and predictably manipulate the Earth's atmosphere, they say, is an act of extraordinary hubris. They call for an international moratorium on geoengineering experiments, arguing that we must not start down a path from which there may be no return. Beyond the scientific debate lie the colossal hurdles of global governance. Organizations highlight immense governance challenges. Who would control this global thermostat? An augmented United Nations body, a consortium of the world's most powerful nations, a private entity with its own agenda? The concentration of such power would be unprecedented in human history. And how would decisions be made? What would be the planet's ideal temperature? A setting that might save one nation from drought could simultaneously cause catastrophic floods in another. How would we compensate the losers in this global climate bargain? The mechanisms for fair, equitable, and enforceable decision-making on a global scale simply do not exist. We struggle to agree on trade policies and emissions targets. To imagine a global consensus on intentionally altering the sunlight that reaches every corner of the Earth feels like a political fantasy. This governance vacuum creates a terrifying geopolitical risk. There is a real fear that nations could deploy this technology unilaterally. Imagine a country facing imminent collapse from heat waves and famine, deciding it has nothing left to lose. It could start spraying aerosols into the stratosphere without international approval, triggering a cascade of global consequences. This could lead to a new kind of conflict, a climate war, where nations blame each other for droughts, storms, and agricultural failures. Furthermore, there's the terrifying concept of termination shock. If a geoengineering system were deployed for decades and then suddenly failed or was stopped due to war, political instability, or technical breakdown, the planet would experience extremely rapid warming, far faster and more destructive than the gradual change we're experiencing now. The resulting climate chaos would be unimaginable. And so solar geoengineering presents humanity with a profound dilemma. It is a testament to our ingenuity, our relentless drive to solve problems and bend nature to our will. Yet it also exposes the potential for our folly, our tendency to create technological solutions that spawn even greater problems. It's the ultimate double-edged sword, born from the same mind that developed antibiotics and nuclear weapons, the same species that composes symphonies and clears rainforests. It forces us to ask a fundamental question: is our intelligence matched by our wisdom? It's crucial to understand that even in the most optimistic scenarios, the technology is not a magic bullet. It is, at best, a form of planetary pain relief that does not cure the underlying illness. Solar geoengineering does nothing to remove carbon dioxide from the atmosphere. The CO2 would continue to build up, and with it, the silent crisis of ocean acidification would worsen. Our oceans would continue to absorb that excess carbon, becoming more acidic, threatening marine ecosystems, dissolving the shells of vital creatures at the base of the food chain, and destroying coral reefs. It would be like taking a painkiller for a broken leg while the bone continues to grind and shatter. We might feel a temporary reprieve from the fever, but the disease would be metastasizing within the system. This is why the overwhelming consensus remains that our primary focus must remain on healing our planet the natural way, by reducing our impact and transitioning to a sustainable existence. The real lasting solution is not to block the sun, but to fix our relationship with the earth. This means a monumental global effort to transition to renewable energy, to reinvent our industries and agriculture, to reforest our lands and restore our oceans. This is the hard, necessary work. It is the only path that addresses the cause, not just the most obvious symptom. The sun gives life to our world. It is the engine of our climate, the source of all our energy, a symbol of hope and renewal in countless cultures. The notion that we might have to dim its rays to survive is a sobering reminder of our failure to live in harmony with our own planet. It's a tragic irony. To save ourselves from the heat we've trapped, we consider drawing a veil against the very star that makes life possible. This uncharted path forces us to confront our role as stewards of this world. It reminds us of the fragile balance we are so close to breaking and the profound responsibility we bear for our planet's future. The choice is not simply about which technology to deploy, it is about what kind of future we want to create and what kind of ancestors we want to be. Do we risk becoming perpetual managers of a planetary machine, forever dependent on a fragile technology to keep our world habitable? Or do we undertake the difficult, transformative work of healing our home, ensuring that future generations can thrive under a bright, undimmed sun? The answer will define humanity for centuries to come.